Now, okay, here we go. Let me just start a new note here. Oopsie daisies. You guys are my Tuesday, Thursdays. Mm-hmm. 002. Cool. Okay, I have a couple of these left. Did anyone not get a term schedule yet? Yeah. No, I have no more. But if you need one, let me know. Okay, great. So good news, guys. When I did this lecture yesterday, we ended a little bit early, so we'll probably do the same. I felt kind of silly because I should have just brought more notes and kept going, but I didn't, so I'm going to do the same thing for you guys, otherwise I get too confused. So congratulations. Can look forward to a slightly shorter class. 2 hours is long anyways, right? So, oh, sorry, 1 hour and 50 minutes. All right, so let's do a little bit of review before, because it was a while ago that we met. So we talked about expanding and factoring. Expanding is when we break out the brackets, right? We expand an expression so that there are no more brackets or anything like that. So I'm going to call it a breakout, in air quotes, the brackets. We talked about, right, if we have something multiplying something inside the brackets, we just have to bring it in and multiply all the terms inside the brackets, and then we've expanded. We talked about factoring. Essentially expanding in reverse, right, where we pull out some common multiple outside and then put the other terms inside brackets, right, to indicate that that's a common multiple. So basically it's expanding in reverse. Okay. Where we collect common multiples to create a condensed equation, right? Factoring, the goal is to create kind of a smaller equation, to create a condensed equation. Bless you. Oh, an expression, all right, just as a little heads up, an expression would be something like 2x plus 4y plus 3, right? Whereas an equation would be 2x plus 4y plus 3 equals 7, right? So the equation is just saying that we have this equal sign in there. All right. Good question. So an expression is just a list of terms, essentially, right? There's no equality. But really good question. Thanks. So, all right. Then we talked about solving systems of equations, and we're actually going to come back to it briefly today, right? And then back to it next day again. So we're going to keep revisiting it, especially in chapter 2, and then we'll probably ditch it for the rest of the course, right? So if you don't like it, just stick with it for a little bit longer. and then it'll be out of your hair. Okay, so we talked about solving systems of equations by substitution. We talked about the elimination method, but then I said, I'm only going to teach you substitution, right? Where we have two equations. I solve for one variable in one of the equations, substitute it into the other one, right? Solve for one of the variables, plug it back in, right? So it's this kind of teeter-totter of substitutions, right? So that's the one I use. And so even if you're going through the textbook and you're looking at the practice problems, yeah.
Sorry. Can you only solve certain equations with substitution, or can you?
No, you can use them for all of them, right? So, oh yeah, so what I was gonna say, so the practice problems, they say solve these by elimination. You don't have to, you can just use substitution for all of them, right? They're just encouraging you to try both ways. I actually don't see a reason you need to know two methods for doing the same thing, so I stick with one. Keep things simple, but yeah. But either method works. It works the same way. Cool. And then we talked a little bit about taxes and other proportions and percentages. Okay. So we talked about taxes and other proportions and percentages. Okay. And we'll come back to that, but later. Okay. What I don't like about these first, maybe even 2-3 chapters, is that it's kind of like all over the map, right? Later on in the course, we'll introduce a topic, talk about it for the whole chapter, introduce a slightly different topic, develop it throughout the whole chapter, right? So it's going to settle down. It's just in the beginning, we need to have all these tools and talk about all these random things, and then we'll settle down and it'll be better. Okay. Unless you love this stuff, then it'll be worse. Any questions for that quick review? No, because we have new stuff to cover, but we will kind of come back to stuff. So like the solving systems of equations we're going to do later today. Yeah. So not to worry. Okay. Oh, and I did try posting on Moodle a link to the video. So hope that works from last day. So if it works, I had someone say, yes, it works. So that's great. So hope it works. And then I'll post the video for today too. Okay. And so on and so forth. So we're into section 2.1, so chapter 2. Yeah. Chapter 2 is on linear functions. Linear functions and graphing. Graphing's kind of fun, so. So, in this course, we'll only graph straight lines, right? So if I say y equals mx plus b, even if you don't think, oh, that's the equation of a straight line, it probably rings a bell from some point in your math career, right? Hopefully. If not, that's okay too. I'm going to tell you right now, the equation of a straight line has the form, and I'm going to use y equals mx plus b just because that's what is usually taught in high school. Okay. Y equals mx plus b. Okay. where, let's do a darker color, where the m is the slope and the b is the intercept. Some other options for writing out the equation of a straight line, things like ax plus b, y equals a sub 0x plus a sub 1, right? All these are options. We could do y equals smiley face x plus sad face, right? All of these, whichever one is attached to the x, that's going to be your slope, right? Whatever is attached, well, unattached, I guess, it's single, is the intercept. Okay, so that's good to know. These are just kind of other ways of writing the same thing. Okay. So where I'm just going to say from here, from that first equation, where m is the slope, okay, or I'll just say in general, right, whatever value is attached to the x, that's going to be the slope. Whatever value is attached to the x. Yeah. Same idea, b is the intercept. And it's just whatever value is on its own. Whatever value is on its own. The intercept, remember, is if you have your x-axis and your y-axis, right? The intercept is where the line crosses the y-axis. Right? So let's keep that in mind. Where the line crosses the y-axis, meaning it's the y when x is equal to 0. So if we imagine kind of a XY axis here, I told you guys how to remember which is the x-axis, right? Maybe, maybe not. Oh, no worries. Did I tell you guys? Someone told me one day, she was like, oh yeah, I can never remember which is the x and which is the y-axis. I said, oh, okay, I don't know, I don't have any tricks to help you. And so she said, oh, well, that's okay. I just think of a little cartoon guy going, no, and he makes an X because this axis is falling on him. So he's going, no. So it makes the x-axis. And I thought that was pretty clever. So, oh, yeah, that works too. We only have to remember one of them, right? Okay. So, you have a line here, y equals mx plus b, right? Whatever the line is, right? This point where it's crossing the y-axis is the intercept, right? Because this point where the axis intersect, right? That's where you're at 0, 0. So here you're at x equal to 0. Okay. So we kind of touched on it last day. We said that if we have an equation with just x and y as its variables, right? So no x squareds and no y squareds, right? No xy's, right? Just x's and y's as our variables. Then we can rearrange it in the form of y equals mx plus b, right? We can move the y to the one side, the x to the other side, and we can collect like terms, and then we have a straight line. Okay? So whenever we have an equation with just x and y variables, okay, we can rearrange it into the form y equals mx plus b. Right. Just a little note, y equals mx plus b, we said is the equation for a straight line, right? Is the equation for a straight line also called a linear equation, right? Linear meaning straight, right? A line. And then an equation, well, is an equation, right? So AKA a linear equation, right? So when you see linear equation, I don't want you to get spooked, right? It's just the equation of a straight line, y equals mx plus b. Okay. Cool. Any questions so far? So, I think graphing straight lines is pretty fun. So let's do it. So, straight lines, yeah. With the exception of next day, but we'll deal with that. It's like a brief exception. Yeah. And I don't expect you to graph anything but straight lines. We'll talk about that's for next day. So to graph a straight line, right, you really only need 2 points on the line, and this is a fact, right? 2 points on the line, and then you can take a straight edge and connect the two, and then the line just extends to infinity and infinity, right? Technically, right? And so we really only need to plot 2 points, connect those 2 dots, extend the line, and there we have it. Okay. So how do we graph straight lines? Okay. So given a linear equation, oops. Given a linear equation, right? We just talked about those, straight line. Like y equals 2x plus 1. We'll keep it simple for just a little bit. We're talking about it. We need to find 2 points on the line and then connect those 2 points with a straight edge. Okay. So we need to find 2 points on the line, okay, and then use a straight edge to connect them. And extend the line. Right, the line doesn't only exist between the 2 points that you plotted, right? Those 2 points are arbitrary. You pick whatever points you want, right? And then you extend the line. Okay. So how are we gonna find 2 points? Right, so we need at least 2 points. I just do 2. We're supposed to do 3, but I see no point because they'll all be the same. Okay. So what I do is my first step is I make a table of at least 2 values of x. I'll do 2. Make a table of at least 2 values of x. Doesn't matter what x you pick, right? You're allowed to pick whatever x you want, but I would suggest picking easy values of x, right? Things that make your life easier. So then, because then you're gonna find the corresponding y values, right? Plug in the x that you picked into your equation for y and solve for y. Right? So find the corresponding y values. Okay. So now you have xy pairs, right? We call those ordered pairs because they have to come in the order of x then y, right? And so you have ordered pairs, and now you can plot those. So plot the xy coordinates. And just as a fact, when we're talking about xy coordinates, they have to be enclosed in round brackets, separated by a comma, right? Just like I've done there. Okay. Plot the xy coordinates, also known as ordered pairs, on a graph. And then, like we said, once we have plotted our points, right, that's when we just connect them and extend the line. Connect the points and extend the line. Okay. So let's actually draw y equals 2x plus 1. I guess this is an example. Okay. So like I said, I'm going to start by making a table of at least 2x values, right? And then I'm going to remind myself that y is 2x plus 1. My favorite x value is 0, right? Easy to deal with, right? Solve for y. So I'm going to pick my first x as 0. So then y is 2 times 0 plus 1, which is just going to be 1. Now, you don't have to show this work for simple things like this, right? But once we have kind of nastier equations there, I think it's a good idea to show your work, right? Just in case something happens. Right? And then what's another nice value of x? 1's nice, 2's nice. For this example, yes, sometimes, usually whole numbers. Yeah. We'll do an example. It'll still be a whole number, but we approach it a little bit differently, right? One thing to remember, you can't pick a wrong number, right? It's just some make your life easier than others, right? We could have done x is 3/7 if we wanted to, right? But why would we want to? Right? So then for the second one, y is 2 times 1 plus 1. Okay. So now our ordered pairs, right, x, y, look like this. 0, 1, 1, 3. Right? Now we have 2 points on the graph. I don't want you to worry about setting up your axes too much, right? I'll give you a graph, and I'm pretty sure I give you the little tick marks as well, right? So you just have to plot your points, right? So you have to know how to find your 2 points and then plot those, right? But don't worry about setting up your axes because I'll have done that for you. Okay. Sometimes it's easy and sometimes it's not as easy, right? So, set up our XY axes. 1, 2, 3, 4. 1, 2, 3, 4. I'm not being too picky about this, right? We're just testing things out. Okay. So our first point, right, is at 0, 1. So 0, 1 would be here. Which is also your intercept, right, at 1. And 1, 3 is our next ordered pair. So when x is 1 and y is 3. Yeah. Oh, no question? So even if I'm in a test, if I need a straight edge, I usually just kind of gently, I don't fold the page over, but I kind of roll it over. Just use the page as a straight edge. You don't have to have an actual ruler, right? It's not that picky. So I just kind of fold it over, draw my line. Right. It doesn't matter. Yeah, it doesn't matter. Yeah, so let's draw this and then I'll show you that it doesn't matter. Okay, so I just set up my page and I connect these dots and I extend the line for as far as I want. There it is. Cool, right? So here is the equation y equals 2x plus 1. Right, and that's the line for y equals 2x plus 1. Okay, so if we hadn't used the 0, that's fine. Pretend for a second that we used x equals 2, for example, then y equals 2 times 2 plus 1, 5, right? So then we're at x equals 2, kind of, boop, 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 boop. I overshot it a little bit, probably because these are not spaced properly, right? But we would end up at 5. Things got a little crooked, but you get the idea, right? So all these points would be on the same line. So it doesn't matter which ones, especially if I've given you a grid, right? You'll want to pick values of x that are in the grid that I've given you. But besides that, you can pick whatever ones you want. Okay. Any questions? No? Comments? Concerns? Great. So let's kick it up a notch. I'm not scared. Example 54. Sketch the graph of 4x plus 5y equals 2. All right. So it's not quite in the form of y equals mx plus b, but we only have x's and y's in there, right? So we can rearrange it. So that's our first step, right? So we're going to rearrange or solve for y to get this in the form of y equals mx plus b. So we have 4x plus 5y equals 2. You'll notice that I always start with my original equation, right? I always write that out, no matter how tedious it feels. Okay. And then, so to solve for y here, we're going to move the 4x over to the right-hand side, right? Subtract 4x from both sides. So we get 5y is 2 minus 4x. Right. And then to solve for y, we have to divide both sides by 5. So we get 2 minus 4x all over 5. Okay. So, right, this is kind of the reverse of subtracting two fractions, because we can rewrite this again as y equals 2 over 5 minus 4 over 5 times x, right? We have this common denominator of 5, which means we can split them up. In fact, we have to have both terms over 5, right? Because all of it's being divided by 5, right? So now, right, we have our slope is negative 4 over 5. And our intercept is 2 over 5. Because, so this is the slope because it's attached to the x, right? We're used to seeing mx plus b, right? The intercept second, but we need to get out of that and be okay with seeing, okay, something like this. Right? You could rearrange it. Right? That's right. That's right. Yeah. So, yeah, so the order of these terms doesn't matter, but whatever is attached to the x, right? Notice I'm including the negative, is the slope, and then whatever's on its own is the intercept. Okay. And so let's just make a quick little note, a little side note here. All right, we can have a negative slope, right, where it's going down. So this is a negative slope. Or a positive slope. So when you have a slope of negative 4 over 5, you know you're going to have this kind of downward sloping line. Right? So that's good to keep an eye out for. So the negative is very important. Right? We can't just drop it or change it or whatever. Okay. So now that we have it in the form of y equals mx plus b-ish, right? We're not too picky. Now we can find 2 points on this line. Okay. So we're still going to find 2 points on the line. I'll set up my table here. And we said y equals 2 over 5 minus 4 over 5 x. Okay. So I'll stick with my favorite x, 0. All right. 0 is, so 2 over 5 minus 4 over 5 times 0 is just 2 over 5, or 0.4 if we want. Just a heads up though, you should only use decimals if it's a nice, neat decimal, right, where you can actually write out all the numbers, right? Otherwise, you should just keep the fraction, right? Things will be lost if you start rounding a fraction. Okay, but 2 over 5 is just 0.4, so that's good. Yeah, it'll be easier with the decimal, right? Yeah. So if you have some nasty fraction, right, like 1 over 3, if you're plotting it, you would just kind of look at what the decimal is, right, 1 or 0.333333333 repeating, right, and just kind of estimate where it would go. Right. So now we need to pick another point, and another point, instead of having to deal with kind of these nasty fractions, right, I might just pick 5, right, because then I have 2 over 5 minus 4 over 5 times 5, but those 5s are going to cancel. So then it's just 2 over 5 minus 4, right, a little bit easier to deal with. Right. So I'm going to pick 5, which puts me at 2 over 5 minus 4 over 5 times 5. Right. But these two 5s are going to cancel. Two over 5 minus 4, okay, which is 0.4 minus 4, negative 3.6. So our ordered pairs, right, are 0, and I'll use the decimals, right, because like you said, it's hard to graph fractions, right, or figure out where they go. Right? We usually just kind of check on our calculator, what would it be as a decimal? And at 5 and negative 3.6. Okay. So here things get a little tricky, right, when I try to figure out my axes, because my x's need to cover at least 0 to 5, right, because those are the points that I've picked. Right, so I have to have x's between at least 0 and 5, maybe a little bit more. And my y's have to cover between at least 0.4 to negative 3.6. So we need to keep that in mind when we're setting up our, but that is part of the reason why I just give it to you. Okay. Yeah, because here you have your, so down here, right, you have your negative y's. So I'm going to try to just use a line. It's pretty faint on there, but a line for 1 unit. Yeah.
Are you going to give us these like on test?
Yeah. So yeah, don't worry, because it is really tricky, and you don't want to get bogged down in it. So 1, negative 1, negative 2, negative 3, negative 4. 1, 2, 3, 4, 5. Okay, so to plot our first point, right, approximately 0, so x is 0 and y is 0.4. I'll just put it here. And then my second point is when x is 5 and y is negative 3.6. So just to keep my kind of eyes straight, those are kind of sight lines, I guess. You don't have to put those on. And obviously I have no idea where negative 3.6 would be, but it would be roughly halfway between negative 3 and negative 4. Okay. So that's good enough for me. So here we're at 5 and negative 3.6. Now we can just connect these two dots and move on with our lives. Oops. So even though it's pretty nasty looking, this is the equation, or this is the line for y equals 2 over 5 minus 4 over 5x. Kind of nasty, but not too bad. Yeah, fractions kind of turn everyone off, myself included. But we can just work through them. Okay. Any questions about that one? Ooh. All right, let's change gears. Oh, I almost licked my finger to scroll here. Ugh. So we'll leave that for a little bit and we'll come back to it next day, right? So next day we're gonna build on this and we're gonna say, okay, well, for our scenario, right, our business scenario, everything has to be, so y has to be greater than 2 over 5 minus 4 over 5x, meaning the only values that are valid are going to be these guys, right? And so then we start graphing, okay, I'm going to undo this squiggly, but I'm just going to show you, right? Then we would only be concerned with that area, right? And then we use that. But that's for next day, right? So we'll come back to this, just keep building on it. Okay. But we need to take a minute to talk about functions, right? I don't know, all through, I feel like high school, I was kind of like, oh yeah, functions. Like I knew how they worked and stuff, but I didn't really grasp what the deal was with a function. All right, so I'm gonna try to take a stab at it, but if you just know how to use them, that's fine too. Okay, so functions. Okay. Take a value, right? Usually a value of x, and return some output value, usually y. Right? So functions take a value of x and return an output value, basically, of y, or in general, we can write f of x. So I want you to read, when I say f of x like that, I want you to read it as, read f of x as f of x. Oops. In general, when you have something like this, right? Function notation, where we have f or any sort of kind of command, I guess. And then in brackets, the variable, you're going to read it as f of x, s of x, right? If you move into stats, we would say something like the mean of x. Scratch that. All right? Oh goodness, should have just erased. There we go. Okay, so f of x, just saying that, hey, here's a function where I need a value of x, and then I can give you an output value of y. Okay? So y is the same as f of x. Okay? So when you see f of x, you can just in your mind read y. Right? That's fine. Mm-hmm. Exactly. Okay. And in our case, we're going to be talking about f of x is mx plus b. Right? We already used this function. Right? We picked two values of x and we plugged each of them in, solved for y. Right? We already used this function. Okay. So I'll just make a note here. Y and f of x are interchangeable as y requires a value of x to be solved. As y requires a value of x to be solved, right? So it is a function of x. Yeah. So we're going to use it as shorthand, right? We use function notation as shorthand. So if I say if f of x is, let's use 2x plus 1 again, find f of 2. Right? Really, what I'm saying is solve 2x plus 1 when x is equal to 2. So we're told that f of x in general is 2x plus 1. Now, in more specific terms, right, f of 2 is going to be 2 times 2 plus 1. Four plus 1. Or if you want to skip to 5, that's fine by me. No. So just like we have, so f of 2, I'll keep going here, is 5. Okay. F of 2, right, is the y when x is 2. Okay. Y when x is 2. Right? No, I'll show you with a graph, right? But if you don't like the graph, you can just sleep for a minute. Okay. So if we have this, this line, let's pretend that this is y equals 2x plus 1. Right? That's our function. Okay. And I plug in a value of x equal to 2. If I map it back to my function, it puts me at f of 2, which is 5. Okay. But like I said, if you don't like the graph, it's just meant to illustrate that we plug in some value of x into our function, and it gives us some of the value of y, right? But if you're okay with just the equation, that's great. Okay. So, any questions before we do an example? All right. Example, let's do 57. Let f of x be 3x plus 1. Find f of 10 and f of negative 5. Give you just part of a minute to do it. So we'll start with f of 10. F of 10 is 3 times 10 plus 1. 30 plus 1, 31. Right. Notice, and I'll kind of start doing it more and more. If nothing's changing on the one side, you don't have to keep writing it out, right? So until something changes, you really don't have to keep writing out f of 10 and f of 10. Yeah.
So what this is just saying is like when x is, wait, no, sorry.
Yep.
I totally forgot how to word my question.
No, I think I got you, right? It's just asking, so when it's saying find f of 10, it's just saying
when x
what
is
is the
10,
function?
y is 31.
Exactly. Yeah. So evaluate the function at x equal to 10. But f of 10 is just way shorter to write. And that's why we need to learn it, right? Because it's just shorthand. But so I kind of, I think, yeah. What if we did f of negative 5? Same idea, right? 3 times negative 5 plus 1. 3 times negative 5 is negative 15 plus 1. Great. Okay. Cool. What if we did something a little bit more relevant to you business peeps? If we do example 60, now I'm saying profit of x, right? This is how we denote a profit function. We all like profit, right? So we need to know how to work with these profit functions. So I'm telling you that the profit of x is 45x minus 725. So that's just the fact for some scenario, right? Okay. So let's say that x is the number of units that you produce, right? Then profit depends on how many, or sell, I should say, right? Profit depends on how many units you sell, right? Or how many hours you work, right? That could be your x, right? Or bill, I should say. Okay. So let x be the number of units sold. Multi-part question here, right? What if I asked you, okay, so if you sell 50 units, what's the profit, right? can kind of handle that. So what is the profit if you sell 50 units? Right? Which really just means that X is 50, right? And so just writing out our general profit function, so I can scroll up here, right? Our profit of any X is going to be 45X minus 725. We want to find the profit of 50, right? X equal to 50. Yeah, we'll get there. Okay, so just plugging in 50 in for X, right? 45 times 50 minus 725. BEDMAS applies, right? So we have to multiply 45 and 50 first. So we get 2250 minus 725. Thank you. So we get a profit of $1,525 if we sell 50 units. Right? That's great. What if we wanted to know, okay, how many units do you have to sell to make zero profit? Right? Because there's costs associated, so we have to sell some amount to even reach zero profit, right? Before we're losing money. So that could be another type of question here. How many units do we need to sell to make $0 in profit? So again, we have our profit function. Profit of X is 45X minus 725. But now I'm asking you how many units, right? Essentially solve for X, right? And I'm telling you the profit has to be zero. So this whole left-hand side, we set it equal to zero, right? We're forcing the profit to be zero, and then we solve for X, right? What X makes that happen? So it's kind of like a reverse, right? We're not solving for the profit anymore, we're solving for the units. Did you guys ever watch the show, The Profit? Anyways, it's really fun. I think it was on A&E or something. He like went into businesses and bought them and then made them turn a profit. It's really cool. It's pretty cutthroat, but anyways, he showed us all how to do it and stuff. Really fun. So setting profit equal to zero, right, then we can solve for X. So 45X minus 725. Solve for X. Right. Just as a little side note. So we have to add 725 to both sides. So we get 725 is 45X. And then we have to divide both sides by 45, right, to get X on its own. And I like to do the switcheroo where I have whatever I'm solving for on the left-hand side. So it'll be the same, but I'm just going to write X is 725 divided by 45. Great. 16.1. Repeating. Now, here's me getting a little nitpicky, right? Because we can't actually sell 0.11 units, right? That's good. Right? And so in order to make at least $0 in profit, right, we would have to sell at least 17 units, right? And so it depends on the scenario here. I'm assuming that the more units you sell, the more profit you make, right? Otherwise, you should probably stop selling it, right? So yeah, it's an assumption, but I think it's fair, right? And so in order to make at least $0 in profit or any sort of positive profit, you have to sell at least 17 units. Right. So technically you only have to sell 16.11111 repeating, but good luck with that. So I'll just make a little note here. In order to make at least $0 in profit, right? Not really what the question was asking, but it's nice to show off your knowledge, right? We need to sell at least 17 units. Cool. How about same idea, but part C? How many units do we need to sell to make $1,000 in profit, right? So if you have some sort of goal in profits that you want to make in a year, right, you have to know how many units do you have to sell, right? So how many units do we need to sell to make at least $1,000 in profit? Oh, question mark. So we're going to start off with our general profit function again. Profit of x is 45x minus 725. Yeah. Exact same thing, right? Now we're just forcing the profit to be 1,000 instead of 0, right? And so we have 1,000 on this side and on the left-hand side, and then 45x minus 725. And again, we're just solving for x. And so we have to add 725 to both sides. So we get 1725 is 45x. And then x is going to be 1725 divided by 45. 38.33 repeating. Okay. So now we have to make at least $1,000. So we have to sell at least 39 units. Right. We would need to sell at least 39 units. Okay. Cool. So we'll come back to profit functions. They're pretty fun in chapter 3, but now you've seen a quick one. Okay. So when we're graphing and working with functions, right, we need to be able to talk about the domain and the range, which you might remember, maybe not very fondly, but we're going to just keep it simple. So we need to talk about the domain and range of a function. The domain is kind of the important one, because the domain is going to be all possible values of x, meaning there are some values of x sometimes that yield illegal math, right? And so what's illegal math? Things like dividing by 0, that's illegal math, can't be done, right? Taking the square root of a negative number, that's illegal math. It can be done, but you have to deal with imaginary numbers, and you can just do 4th year math if you want. But we're not going to do that, obviously. So if you get to some point where you're trying to take the square root of a negative number, I can guarantee you did it wrong. Okay. So the domain of a function is all possible values of x. Okay. So the domain will not include values of x which yield illegal math, Okay. So I shouldn't say prime because that's a math term, but illegal math, kind of the prime suspects. I won't write it down because I think when we say it, it makes more sense. But prime is a type of number, right? Only divisible by 1 in itself. Who cares? I know. Illegal math. Number 1 offender, division by 0, right? Division by 0. So if you have an x, right, doesn't necessarily mean that x is 0, right? But it just means that if you have an x that makes division by 0, it's out, right? And so the second one is if we're trying to take the square root of a negative number. So those are things to look out for. For example, if you have 3 divided by x plus 1, right, then x equal to negative 1 can't be in the domain, right? We can't have x equal to negative 1 because negative 1 plus 1, 0, trying to divide by 0, right? So that's what we mean by x's that yield illegal math, right? So x equal to negative 1 is not in the domain. Because we would be trying to divide by 0, right? Or the square root of 2x minus 4, right? X would have to be greater than or equal to 2, right? So x can't be less than 2. right? Because then you would get a negative number. Try x equal to 1, for example, right? 2 times 1, 2 minus 4, negative 2, uh-oh, right? I'm not going to get you to do those, but it's just good to keep in mind, right? That it doesn't have to be that x is negative or that x is 0, right? Division by 0. We can get there other ways. Okay. The range is a little bit easier. The range of a function is just all possible values of y, right? If the domain is all possible values of x, which it usually will be, then the range is always all possible values of y, right? And so the range of a function is all possible output values of y. So for the most part, right, the domain's going to be all x's and the range is going to be all y's, right, for our straight lines. Okay. Different topic for non-straight lines, right? That's okay. So let's do those are the only examples that we're doing for the domain and range. Let's do a random example, just dealing with functions again. A little bit different, right? In this one, we're going to come back to in chapter 3, okay? If I give you a function that says the future value is the present value times 1 plus lowercase I to the power of n. We're going to deal with this one a lot, right? So it's going to become familiar. This is our first time probably seeing it, so that's okay. We have how many variables? We have the future value, the present value. I'm going to tell you right now, this is the yearly interest rate. And this is how many years we've been invested for. Right? So we have 4 variables, and we can solve for any one of these 4, right, given the other 3. Right? So if we know 3 of them, we can solve for the 4th one. Okay? So we have 4 variables, and given 3 of them, we can solve for the 4th. Okay. And that's kind of how this course is going to go, right? I'll give you a formula like this, and then we talk about how do we solve for each of these, right? What tools do we need to solve for each of these 4 variables in this case? Okay. So here, the future value is, well, it's just the future value. Present value, PV, Puerto Vallarta. Present value. Okay. And so just looking at these 2, I invest some present value today, right? Or potentially in the past, right? And then it sits there for some amount of time at some interest rate, and it yields some future value, right? So that's the time value of money, right? We invest some amount, and then it's going to grow at some rate for some amount of time and yield some future value, right? And so we might want to find how much do I need to invest today if I want to have $5,000 4 years from now, right? Or if I invest $4,000 today, how much am I going to have at this time next year, right? That kind of thing. So I, lowercase I, is going to be the yearly interest rate. Yearly interest rate. And lowercase n is the number of years that this has been invested for. Number of years invested. So if I say something like, if an investor invests $1,500 at a rate of 6% per year, what is the value of the investment, right? What's the future value? What's the value of the investment after, and I'm going to change the textbook example from 6 years to 7 years. You'll see why in a sec. At a rate of 6% per year, what is the value of the investment after 7 years? I wanted to change, so the textbook example has 6 years, but I didn't want it to get too confusing with the 6% and the 6 years, so I changed it to 7 years. Doesn't matter. Okay, so jotting down our formula, right? The future value is the present value times 1 plus I to the power of n. It's just a matter of plug and chug, right? Once you read this and you identify that, okay, so the initial investment was $1,500, right? The 1,500. So that's going to be your present value. And then the interest rate of 6%, keeping in mind what we learned the other day, where if we're working with percentages, right, we have to convert them to decimals, right? And then it sits there for 7 years. Okay? So we're trying to solve for our future value. The future value is the present value we decided was the 1,500 times 1 plus 0.06 to the power of 7, right? 7 years. So I'll just make a little note here, right? The I must be in decimal form. Otherwise, we can't math it. Okay. So now, BEDMAS applies, right? We have brackets, so we start inside the brackets, and then we deal with the exponent after, right? Brackets, exponents, division, multiplication, all that fun stuff. So we leave the 1,500 on the outside, and we simplify inside the brackets to get 1.06 to the power of 7, right? 1 plus 0.06. And then we do 1.06 to the power of 7. Thanks. Leaving the 1,500. And so do you guys remember how to do 1.06 to the power of 7? So you get 1.06 on your screen, and then hit the Y to the X button. It's kind of by your or between your division and your multiplication. Right? And so Y to the X and then to the power of 7 equals 1.503630259. let's see here. 1.06, maybe I did it wrong. 1.503630259. Oh, we'll change the number of decimal places. Right. Oh, weird. There you go. I don't know what was going on. Remember, we said that you don't have to write out all your decimal places. I'm just doing it for you to check that your calculator is actually producing what mine is. Right? You want to double check that. Okay. If you want to only write out 2 or 3 decimal places, that's fine. But you have to keep all your decimals in your calculator. Right? So for your final answer, I'll expect you to have kept all your decimal places. And then now we can just multiply that by 1,500. $2,255, and I'll do the full decimals here so you can check them, right? And 445,388. Do you guys know the approximately equal to, right? If you're rounding, now that's pretty picky of me. It's not something I'll be looking for. If you do straight equal signs, it's fine, right? But the squiggly equals just say approximately equal to $2,255.45. Hello. Thanks. Okay. So the future value would be $2,255.45. Okay. Cool. All right. So let's just briefly talk about supply and demand curves, right? If you're doing any sort of econ, you've probably seen them at some point. Not really my job to teach them to you either, right? But what we said before was our supply and demand curves, right? That's the reason we want to be able to solve systems of equations, right? Because we want to find that point of equilibrium, okay, where everyone's happy. So we'll do 2.2 supply and demand economics. Okay. See. So things get a little bit different, but basically the same as what we've been doing, right? Except we're going to replace the X with the quantity and the Y with the price, right? Because regardless of which side we're on, right, we're going to be talking quantity and price. Right? And so we have something like this. So our price goes on the y-axis and our quantity goes on the x-axis. Okay. Now here, your demand curve, denoted by a capital D, is always going to have a negative slope, right? It's going to be negative. If you have high prices, right, demand is going to be low. If you have low prices, demand's going to be high, right? So your demand curve is always going to be negative. So demand curve has a negative slope. Whereas on the other end, right, the supply curve is going to be positive. Right? Shorthanding these just P and Q instead, price, quantity. Our supply curve is going to have a positive slope, right? Because if the price that they can charge is low, then, right, they don't want to sell too much. if the price is high, they want to sell a lot of stuff, right? Or then the supply is high. So supply, or the supply curve, has a positive slope. So we said last day, right, that the point of intersection, that's the point of equilibrium. Okay. So the point of intersection will be the point of equilibrium. The point of equilibrium. Okay. So in a general scenario, we've got price and we've got quantity here. We've got a demand and a supply curve. Okay. This point here, right, represents some quantity at equilibrium and some price at equilibrium. Right? That's the only place that everyone can agree. Right? Everyone's happy. So this is equilibrium. Okay. So the supply and demand curves, right? They're straight lines. So they'll have linear equations, right? Linear functions. And so we can solve a system of those two equations to find the point of equilibrium. Right? And so since S and D, right, the supply and demand curve will be linear equations, we can solve the system of equations to find the point of equilibrium. Let's do an example. So find the point of equilibrium when it's going to be set up a little bit differently, right? When the supply curve has the following equation, Q equals 2P. We've replaced X's with Q's and Y's with P's. Doesn't really matter, right? And the demand curve is Q equals 10 minus 3P. Okay. Solving this, right, we use the same method. In fact, it's nice because both of these are solved for Q already, right? So it's even easier than it was before, because before we had to solve for one of the variables and then substitute it back in, right? And so we can say that, okay, well, I'm going to let this be equation 1 and this be equation 2. Okay. You can ignore the S colon and the D colon because those are just statements. It doesn't actually matter, right? And so I'm going to substitute, well, I'm going to substitute equation 1 into equation 2. So yeah. Substitute 1 into 2. Q equals 2p in equation 1. So I'm going to put Q equals 2p in for Q in equation 2. So I just get 2p equals 10 minus 3p. That's nice. Right, we just set them equal to each other because they're both equal to Q. Yeah. Now we're going to solve for P, right? P is the only variable left, so we're going to solve for P. So I want to move P's to one side. I'm going to add 3p to both sides because I don't like negatives. Right? So I'm going to have 2p plus 3p is 10. So I have 5p is 10. So p must be 10 over 5, or if you just wanted to skip to 2, that's fine by me. So the price at equilibrium is going to be $2 whatever dollars to potentially $1,000, $200, to something, right? Whatever the units are, it doesn't matter. And then we remember, since Q is 2 times P, right? Q, I'll do it. Q is 2 times 2 at equilibrium. So Q must be 4 when P is 2, right? Q is a function of P. Okay. So therefore, the point of equilibrium is when the price is 2 and the quantity is 4. Any questions about that? Cool. All right. Well, that's all I've got. So have a great afternoon. I'll see you on Thursday. Yeah. Oh, that, but did you have a question or no? Yeah? Say that again? No. No, not in this course. Probably for other courses, but no. Yeah. Yeah.